Okay, I think we can start. Good morning, everyone. Welcome to today's Epicure webinar, From Traces to Optimization with NVIDIA Nsight Systems on heterogeneous HPC platforms, which is the fourth of 5 sessions in our webinar series on profiling, designed to guide you step by step through the key concepts and tools of parallel performance engineering. My name is Isabel Rio Torto. I'm a researcher at Inesctec, also associated with the Epicure project, and we're delighted to welcome you and talk about profiling. So our speaker today, who I would like to start by thanking, is Laura. Laura was originally trained as a physicist, specialized in high-performance computing during her PhD in physics and nanosciences at the University of Modena and Reggio Emilia. Since 2021, she has been a member of the high-level support team at Cineca, where her work focuses on porting applications to GPUs. She maintains a focus on balancing performance with code maintainability and portability, viewing profiling as an indispensable tool for achieving effective and sustainable optimizations. So, I would just like to inform you that you can and you should interact during the presentation. To do so, you can use the chat to share your questions, and during the presentation, there will be no discussion moments, but at the end of the webinar, we'll have some minutes to discuss all the questions and interact directly with you. I will be monitoring the chat activity regularly, ensuring that all questions are dealt with by the speaker at the right time. And some useful information. Please keep your microphone muted during the session, so to prevent background noises. Please turn it on only when needed or asked. And the session will be recorded and you will have access to it in the end. So now we can move on to the presentation. Thank you so much, Laura, for agreeing to do this webinar, and the screen is yours.
Thank you for the introduction. I will switch off the camera to minimize the latency. So, okay. And now I'm going to share the screen. So I hope you can see the screen.
Yes, perfect.
Okay. So first of all, I will describe a bit the agenda of today. We will start by looking at some common bottlenecks of single GPU programming. And then I will show how to implement a performance engineering workflow with NVIDIA Nsight Systems tracing tool. Then we will discuss how to visualize asynchronous programming and multi-stream in the timeline view of Nsight system, how to check for awareness in MPI communications, and I will finally provide some examples of the usage of Nsight system from our support activity. One disclaimer, the presentation is based on the OpenACC offload model, but everything we cover about Nsight system applies regardless of the underlying offload model. So let's start with common bottlenecks. When we discuss offload to GPUs, we have to take into account that nowadays computation is heterogeneous programming. So basically, this means that we have on the same node, one CPU and a number of GPUs. The CPU is characterized by several strong cores, which are highly specialized for serial processing, orchestration, I/O. And we also have these GPUs, which are characterized by many thousands of cores, and these can provide massively throughput for highly parallel workloads. So in the standard GPU float model, you typically have a code which starts on the CPU for this initialization, for example, and then the most compute-intensive function and lines of the code will be offloaded to the GPU, and then the computation will go back to the CPU for some, for example, I/O operations. We also have to take into account that the GPU needs to have the data on its own memory in order to compute. So I will show in the next slide how the CPU and GPU interaction is typically visualized in a timeline view. And in particular here we have on the x-axis time and on the y-axis location of the different events, which are, let's say, happening during the program runtime. So on one line, we have the events on the CPU. On the other line, we have the events on the GPU. So the program starts on the CPU. Then at a certain point, it enters an offloaded region. Then we need to push the data from the CPU to the GPU in order to compute such data, to operate on such data on the GPU side. Then we also need to launch the operation to be done on the GPU. And this corresponds to a sort of an amount of time which is spent on the CPU side to launch the kernel, okay? And then some other time spent on the GPU side to actually execute the kernel. For OpenACC, for example, which is synchronous by default, then we have also some time spent on the CPU side to wait for the operation on the GPU to be done. Then the data is eventually downloaded from the GPU to the CPU, and this corresponds to a record both on the GPU and the CPU side. Now, OpenACC is asynchronous by default. Of course, if you're using CUDA libraries, there is no wait status because these programming models are asynchronous. So now the very first bottleneck that we can encounter when we offload our calculation, our program to GPUs is related to data movement, because the program starts on the CPU, GPUs and CPUs have separated memories, the GPUs need data in their own memory, and the I/O bus is low compared to the GPU bandwidth. So moving data is expensive. Consider, for example, the previous picture, and now in a situation where the blue part, which is the computation, is taking a short time with respect to the green and purple regions, which are related to data movement. And assume that this kind of pattern is inside a loop. What you will see on the timeline in this scenario is something like that, where you have most of the time on the GPU side spent in moving data than actually doing calculation. So to fix this, we need to improve the data locality, which means avoid move the data in and out the GPU around the kernels, the kernels or the OpenACC, OpenMP loop, but try to move the data at the beginning and at the end of the whole offloaded region. Basically, you should achieve something like that, where you have data movement at the beginning, upload of the data at the beginning, download of the data at the end, and in the middle, mostly computation, blue events, okay? Now, second consequence of the fact that the GPU offload is implemented in heterogeneous node. So the program starts on the CPU. There are many ways to float kernels to GPUs. You can use OpenACC, you can use CUDA libraries, OpenMP, but there is always a latency between the launch of the kernel and its execution on the GPU. This latency is called kernel launch time. So on the timeline, you can visualize this as a gap on the GPU side, because you see that in the case, if you have a kernel which takes a short time to be executed on the GPU, and a short time with respect to the time taken to launch the kernel itself, then you might have, and you consider this kind of pattern inside a sort of loop, well, you can see that you will spend on the GPU side more time to wait for something to do than actually computing. So this basically is called the GPU starvation, and reduces the performance on the GPU side. So the solution is to try to expose to the GPU as much parallelism as possible. This might mean to refactor a bit your loop, or eventually move the parallel OpenACC parallel loop, ACC parallel loop on an outer loop instead of an inner one. This depends, of course, on your program, but typically what you want to achieve is a configuration like this one, where you have a kernel on the GPU side, which where the computational time spent to actually execute the kernel is larger than the time spent to launch the kernel. So let's now enter into the topic and discuss how you can use Nsight system. So first of all, Nsight System is a particularly useful tool in this context, in this scenario of heterogeneous programming, because it provides an holistic view, and you can visualize on the same timeline both the activity on the CPU and the GPU. It provides information not only on data movement, but also on very nested bottlenecks related to latency, synchronizations. We will see also awareness in API communications. And also because you can use Nsight System on distributed programs. So some of the interesting events that you can intercept with Nsight System are CUDA APIs, OpenACC regions, MPI OpenMP instrumentation. You can also instrument the GPU kernels. You can do CPU sampling and also sample the network metrics. Regarding the technique used by Nsight System, it combines sampling and instrumentation, and it provides mainly traces, timeline views, but then you can also post-process them to generate summaries. Nsight System is available from the NVIDIA HPC SDK compiler or the CUDA toolkit. Okay, how to use Nsight System? So first of all, you need to invoke the daemon nsys. And then you have to specify the what you want to do, what you want to do with nsys. Today we're going to see nsys profile. nsys profile basically launches the measurement when the application run starts. Then you have to specify what you want to profile, and then you add the executable with its arguments. So regarding the optional command switches, you can see, for example, the most basic one is minus trace. With minus trace, you can specify that you want to instrument CUDA APIs, cuBLAS, NVTX, MPI, OpenACC, OpenMP, or many others. You can check from nsys profile minus help. But in addition to minus trace that we are going to use today, you can also add minus backtrace to choose the backtrace method for CPU sampling, CUDA memory usage, which can be used to see the usage of the memory from CUDA on the GPU side, NIC metrics for the infinite band bandwidth, and you can also have some switches which are interesting if you are working with a Python program. Indeed, Nsight System supports Fortran, C++ program, but also Python codes. A good practice to use Nsight System is to profile short runs. So typically, these short runs can be maximum 5-10 minutes. This actually depends a lot on the amount of events that you are measuring. And also the number of processes, if it is a distributed run, that are involved in the measurement. One suggestion is to focus on a subset of events that are relevant for your use case, and also apply filters to focus the measurement on the relevant part of your code. And we will see how to do that with NVTX ranges. Now, the demo that I'm going to show you for the performance engineering workflow with Nsight System will use a simple toy code offloaded with OpenACC in Fortran, but the same analysis applies to any programming model in C++ and also Python. So instead of showing you a snapshot, I'll open the GUI now to show you how a typical timeline view looks like. And this is a code ready for production. Now you can see that Nsight System provides a timeline view where you have on the x-axis time, on the y-axis location. Okay, so these are the location of the different events that are present in the timeline. For example, let's zoom on a region. Like here, we can see what is happening on the CUDA hardware, which is the GPU, and NVIDIA 800 this is a run on Leonardo. Then you can also see the event, the instrumentation of the MPI API, the instrumentation of the CUDA API, etc. Now, of course, reading this report can be a bit complicated, but we will see how to improve the readability with NVTX ranges. Now, I want also to show you an additional kind of information provided by nsys. In this analysis summary, you can find, say, a list of some information related to your run. For example, the command line, which is very useful, for example, if you want to share traces with other people. Then you can also see a description of the hardware available when profiling your code. And then you can also have the percentage of time spent in the different, let's say, modules called from the program. And also, this is very interesting, a list of all the environment variable and their value set at runtime. Okay. So, in addition to that, you see that here, basically, there are different traces. Some of these are provided by instrumentation. Some other are provided by sampling, like this sampling point. And then from sampling, you can also extract flat view, which are basically flat profiles, where you can see the different even organized by self-time or stack time. Exclusive time is if self, and inclusive time if stack. Okay. As I said, reading these traces and especially understanding the algorithm of the program is quite difficult. And especially, and if we want to focus on a specific event, like for example, this kernel on the GPU, it is difficult to understand from which routine the kernel has been called. And this is why you can add NVTX ranges. Now, this is exactly the same run and the same code. Now we have added NVTX ranges in the source code. You see that now the algorithm is much more easy to understand. I see that the code is doing some initialization here, some other computation here. And if I want to identify the portion of the source code from where a specific kernel comes, I can better get this information from the NVTX ranges. Okay, so, but let's see more in detail how to read, how to generate these summaries and to read them. So to do that, as I mentioned before, we will use a very simple toy code. Basically, this toy code is composed by mainly two functions. One function, mainly two files, is better in Fortran. In one file, there is a do loop. The do loop basically calls one routine with some computation, and then it computes an error by reduction. It checks the convergence. It does a copy on a temporary buffer, and then it continues the loop. Otherwise, if it has reached the convergence, it exits the loop. Okay, so this is a very basic standard code, but which is very good for this purpose. Now, let's see how to do a, let's say, first porting assisted by Nsight system. So let's start with the serial version of the code. Now, I won't enter into detail the source code. You will find all the source code available on our GitLab repository if you want to reproduce this demo. But now you just need to know that if I want to profile this specific code after compiling, I need to use nsys profile, as I mentioned before. I can specify what I want to trace, minus trace equal, for example, the runtime library of the operative system. Of course, this is a serial run, so I won't see much on the timeline. I also specify this backtrace method for CPU sampling, and then I just add the executable and some arguments for the executable. Okay. I submit my JavaScript, and then I look, and this will generate a report with an extension, which is nsys rep. Okay. Then I open the report from the GUI. In this case, I've installed the GUI on my laptop. File, open, and then you can open any report generated on a cluster, for example. Then what you will see is this. So basically here you see that there are not many information. We see here some events provided by instrumentation of the OS runtime libraries, many F-writes, so probably here there is an IO phase at the end of the program. I can also get some minimal information from the sampling point here. For example, here I see that the code is calling in this region most of the time this delta SQ Jacobi step ECC. I can get some summarized information from sampling by using the flat view. I can organize the time by self. So, okay, most of the time in my code is spent in Jacobi step ACC, this other IO operation. Be careful when you use flat view because this is an information provided by CPU sampling and generally speaking sampling. And of course, it is affected by statistics. So eventually, if you have a short run, maybe you need to change the sampling frequency, or short event, you have to change a bit the sampling frequency. But however, I want to improve the readability of my timeline. So I want to add these NVTX ranges. So let's see how to do that. Let's go back to the presentation. Now, NVTL and NVTX library and the NVTX ranges come from the NVTools library. This can be used to enhance the tracer readability. These are C-based API that you can use to annotate code ranges, then visualize those ranges in the Nsight system timeline with a given label, with a given name. Okay, they typically add a limited overhead. And if you are using, if you are working on a C++ program, the APIs are these NVTX range push A, NVTX range push W, or NVTX range push X, depending on the argument of the API. A and W are used if you want to provide to such ranges just a label, just a name, without any difference in the coloring. NVTX range push X requires a more complex input, which is a sysstruct. This struct has to, in this sysstruct, you have to define more information, like, for example, the version, the size, in addition to the message type and the kind of message. And you can also, but you can also specify the color. And in this way, on the timeline, you will see also different colored ranges, like in the one I showed you before. And then to close the range, you can use the stopper NVTX range pop without any input. This will automatically close any previously opened range. This is an example of how you can use these ranges. Basically, if you have some portion of the code that you want to name with a given label, you just need to wrap this portion of the source code with NVTX range push A and pop, or push W, or push the X. Okay. Now, for Fortran programmers, basically, there is an interface, a module, the NVTX module, which is already contained in the NVHPC SDK compiler suite. This module contains interfaces to the C-based APIs. So in this case, you have to use subroutines called NVTX start range and NVTX end range. And in this case, you can specify the string. You need to specify at least one string, which corresponds to the name of the label that you want to provide to the range, and then one additional parameter, an integer, to set a specific color. Okay, this simplifies a bit the definition of the ranges with respect to the C++. And this is just a slide which shows how the NVTX.f90 interface file is written, but you just need to compile with -lib equal NVTX, and you don't have to define with the latest version of the compiler. You don't have to define the Fortran interface manually. Okay, so let's see now how to integrate this in our code. So let's go back. Example, now I have added to my source code, all the ranges. For example, here, I want to wrap my loop with NVTX start range main loop. Then I want to close the loop, and I have also to add NVTX end range. I add some other ranges for the penalization, and I add some other ranges. In the for the Jacobi step routine and for the delta SQ reduction. Now, I have to launch again my profiling session, nsys profiling, in this case, minus trace. I also add NVTX because I need to tell the daemon that I want to intercept NVTX ranges. Actually, by default, if you don't specify any minus trace, nsys will automatically profile operative system runtime library and NVTX and CUDA. But I prefer to be verbose, so I add this comma NVTX. And then I generate the report 1.nsys rep, and I open it in my GUI. This is how it looks like. So now you can clearly see that in my code, there is one final phase of finalization, which is taking along much of the runtime. And then the interesting part, the part that I can and I want to offload, is this main loop. So now the point is maybe now this is a toy code. Maybe I have a bigger code that I want to work with, and I need somehow I need some way to focus my measurement on main loop only. And to do that, I can use the NVTX ranges without recompiling and modifying the source code. Because now I can tell to the profiler, hey, profile measure only the main loop without all the rest. And to do that, you just need to change the command line for the profiler by specifying a profiler capture range NVTX and NVTX capture main loop, which is the range that I want to measure. You submit your job, you get the report, you open the report again, and then that's it. So you see that now in our trace, we only have measured main loop. You have also the other ranges, the one in the Jacobi routine and the Jacobi subroutine and the delta SQ subroutine. Of course, ranges can be nested, as you can see. And now I can actually start my offload. Of course, this is a toy code, so very small, very simple, but maybe you have a real production code that you want to optimize. And this is very useful if you want to focus on a given phase without having to reduce the size of the system, because this might change the performance. So you can just add NVTX ranges and then filter the program execution in order to measure only that portion of the code without changing the input system or any other characteristics of your code. Okay, so now I start doing some minimal porting with OpenACC. Okay, first of all, I've understood, if I look at the flat view again, basically now I can see I don't have anymore any information related to the I/O phase because this has been traced out. But I can see that, okay, most of the time is spent in this Jacobi ACC and Delta SQ. I want also to show you that you can generate statistical stats, which is summaries for different events instrumented with minus trace. For example, here we can have an NVTX range summary, which basically provides, you see, some summarized information related to the NVTX ranges. So clearly we can see that most of the time here is spent in executing Jacobi and Delta SQ. So we start focusing on porting these two regions. So in this example, I have offloaded this double loop with an nsys parallel loop collapse, and then the Delta SQ with an nsys parallel loop collapse reduction. Now I'm using OpenACC. I know that OpenACC can handle data movement automatically, implicitly. At this point, I have to tell to the daemon that in addition to trace to trace NVTX, we also need to trace OpenACC. Actually, by tracing on OpenACC, CUDA is traced by default, but here we prefer to be verbose, then we add also CUDA. We resubmit the job script, we generate the report, and we look at the report. This is how the report looks like. Okay, so if I look at the time spent in main loop, I can see that from 7 seconds now, the time is 8 seconds, more than 8 seconds. So my offload is not performant at all. I want to understand why. So first of all, if we now you see that we have a new row. This row corresponds to the CUDA hardware because now GPUs are active, are working, and we are instrumenting, we are tracing also the activity on the GPU side with this OpenSCC, CUDA. Okay. Now, if we open this, let's say, list, we can see that a very small percentage of the time on the GPU is spent in kernel computation and a bigger amount of time is spent in memory. Let's try to see why. Now, here there are many iterations. I will focus like 1, 2, 3, 4 iterations. I will focus on a couple of iterations. Iterations are characterized by Jacobi, delta, and the gap. Jacobi, delta, and the gap, which is probably something else inside the loop, which is taking time. Now, if we look, let's focus on Jacobi. Jacobi is the offloaded routine with the OpenSCC. So inside Jacobi, here we have a very small amount of time. Here is on the OpenSCC row, okay, on the OpenSCC row. The nsys profiler has intercepted this event, this region, which is a compute construct from the source code file in the source code jacobi.f90 at line 23. This is basically my parallel construct that I've added manually in the source code to offload the region. And you can clearly see that if I click, this corresponds to some event on the GPU side. This is the GPU side, and this is the side of the CPU and related libraries. So GPU side, we have this kernel. You can find some information related to how the kernel has been executed in terms of grid and block sizes, for example, and other metrics. But basically, this kernel is taking this amount of time, okay, which is small compared to the time spent in this green and red event, which are, if you put the cursor inside, will tell you which are data movement. This is a main copy, host to device, and this is a main copy, device to host. This main copy generates from here, from this OpenSCC enter data, let's say directive, in file jacobi.f90 at line 23. This enter data is actually now an implicit data movement that has been generated by OpenSCC. OpenSCC handles data movement implicitly. OpenSCC looks for data on the GPU. If the data is not on the GPU, the data is uploaded and then downloaded. If you want to know which data has been uploaded, just put the cursor in queue upload. You see the variable name here, psi. Here you can see the variable name for the data downloaded, psi new, okay? And if you check this for also delta SQ, you will see basically that the same issue arises. So now that we have, you see basically that here we have a lot of time spent in data movement. So what we want to do now is to fix this issue. So to fix this issue, we need to handle data movement manually. So let's optimize reporting. To optimize the porting, I need to add some data directives in order to copy the data only at the beginning and at the end of the loop and avoid the runtime to copy data at each occurrence of Jacobi delta SQ. Of course, I also have to offload this additional portion of the code, which was not offloaded and which was providing this gap. Because you see that if you see a gap here, it means that there is something happening on the CPU which has not been offloaded, like in this case. We don't have any activity between the delta SQ and the next Jacobi. And this is exactly this copy back. Okay, so we implemented this optimization, we regenerate the report, and we open it in the GUI. This is what you see. So now you actually see a main loop which is taking 500 milliseconds. So we have improved significantly our offload. And also the Nsight system tells you, okay, you are now spending 56% of the time in kernel computation, 44% of the time spent in memory, data movement, because you're moving the data only before and after the loop. So one information. So if you look here in main loop, you can see this OpenHPC profiling initialization. So be careful when you instrument, when you measure, use this capture range and NVTX on very small ranges, because the tool will attach somewhere the overhead for the OpenHPC profiling, so for the profiling initialization. Okay, and this overhead can become visible if you have short loops, short ranges. Of course, this was present also here, but we didn't notice because it was a small overhead compared to the time spent in the main loop. Now, if you look at the timeline, this is very visible, but maybe you don't open the timeline and you rely only on the NVTX range summary. If you rely only on this without looking at the timeline, basically you will end up in having a total time for the main loop, which is actually overestimated with respect to the actual duration of the main loop. So be careful with the short measurements because of the potential overhead of the tool. Okay, so let's now, the slide basically recap a bit what we saw. So far I showed how to generate a statistical summary from the GUI. You can actually generate a statistical summary also from the command line. To do that, let me load the NVIDIA SDK compiler. You just need a nsys report. And this generates some report here, for example, OpenHPC, and a report, a summary of all the OpenHPC event intercept. If you want some non-default report, you can use help report. And for example, generate a report for NVTX, for CUDA, and other events, many other events. So now let's move to the second topic, how to use Nsight system to assist asynchronous programming, the implementation of asynchronous programming and multi-stream. So, so far I've used OpenHPC in synchronous mode, which means basically that this is the default mode of OpenHPC. So basically the CPU blocks the activity until the kernel finishes to be computed on the GPU side. But it is also possible to, and this is actually the default in other programming model, to use an asynchronous approach, which means that the CPU moves on immediately and the GPU executes in the background. So this gives us the possibility to implement also multi-stream and overlap some activity on the GPU. Let's see how. In this example, we want to calculate this field A, field B, and then calculate the sum of the A and B arrays. To do that, we can consider an asynchronous approach. If we apply an asynchronous approach, we need to populate A, then populate B, and then calculate the sum. But if we assume to implement an asynchronous approach, we can populate A and B at the same time, and then compute the sum of A and B. So this on GPUs, this is possible because the GPU has different queues called the streams, where you can launch your kernels. So in the previous example, we can consider to launch the first kernel, filling of A, asynchronously on the first queue. Then we can launch the second kernel on the second queue. Then, and this can be done in OpenHPC, for example, using async clause and in bracket the number of the streams. Then I can also I need to put a wait status on the queue number 2 to wait for the operation on the queue number 1, on the stream number 1. And finally, I can push the final sum on the stream number 2. Eventually, I will download the data asynchronously from the stream number 2, and I put a wait status, which blocks the activity until the operation on the GPU is done. So, and this is an example of how you can overlap computation with computation. Another example is overlapping computation with data movement. Assume that you have, let's say, two independent operations which are serialized and are characterized by an host to data, host to device data movement, kernel computation, device to host, and then another operation, host to device, kernel, device to host. Now, if you use asynchronous programming, you can basically overlap host to device data movement of the second operation with the kernel computation of the first one. Let's see with a simple example how to check for the implementation of asynchronous programming with the Nsight system. So you will find also this Mandelbrot example. I will not enter into detail regarding the source code, but basically here you have one file which contains this double loop. Okay, this double loop is initially flooded as a single kernel. A buffer called image is filled by the output of a routine, which is offloaded to GPUs. We already control the data movement manually with this ACC data, and then this is a single kernel launched on the GPU. Let's have a look to how it looks like on the timeline. Now, this is our CUDA hardware. Here I'm running on Leonardo, so NVIDIA 164 GB. If I open the CUDA hardware, I can clearly see that I have firstly this kernel computation and then my copy out, because I need to download the data from the GPU to the CPU to do some IO operation. This is indeed a device to host main copy. Okay. Now, of course, this kernel has been launched in a synchronous approach. Here you have the wait status. Now, let's assume to change a bit. Let's change a bit the algorithm. We change the algorithm as follows. So we basically divide the width dimension of our two-dimensional grid for the image, for the buffer image, into blocks, into chunks. And we add an outer loop where we implement this operation per chunk. Okay, so we define the starting index, ending index, and then we reduce the double loop on the local domain of each chunk. We launch one kernel per chunk, and then instead of having a final copy out, we update only on the CPU, only the portion of the chunk that has been computed on the GPU side. We generate the report, and we look at the report, and this is how the report looks like. Now, computation, data movement, computation, data movement. If you look at the runtime, this hasn't changed much. Of course, we are just splitting kernel computation into smaller pieces, data movement into smaller pieces. What we want to do now is to overlap this data movement with this kernel computation as they are totally independent. To do that, we go to the next example. We use the async clause, for example, in OpenCC. And with this async clause, we launch each block on stream 0 or stream 1 according to the block index, if it is even or if it is odd. Okay, and we do the same also for the update, of course, because we need to update from the stream where the portion of the block has been computed. Let's have a look to how the report looks like. So you see here now that you have here for each stream what is happening on each stream, which kernels are running, which data movement for stream 17 and for stream 18. And you can clearly see that here the data movement overlap with the computation. Data movement overlap with computation and so on and so forth. You can also see some gaps, probably because here the computation is taking too long with respect to the amount of time spent in data movement. And this might suggest you maybe I have to increase the number of queues, change the block size in order to improve a bit the performance of this, improve a bit the performance and the overlap of this data movement and computation. You also see that now here our compute construct launches the kernel kernel asynchronously, and it does not call any wait status. So this one, here you have the compute construct. This is asynchronous, no wait status, okay? And the operation is executed on the GPU far away, let's say not exactly here in the compute construct region. Okay, now this is a bit of information on how you can use Nsight system to check for asynchronous programming and efficiency of overlapping computation with data movement in multi-stream applications. Now, let's move to the next topic, awareness in API communication. So you can distribute computation on multiple GPUs in different ways. In this webinar, I'm referring to MPI jobs. So in MPI jobs, typically you will initialize MPI, you will bind each MPI task to one GPU, and then at a certain point you have to handle communication. So let's assume a first naive approach. So we have two processes, you see, binded to a GPU, each process has offloaded its own computation to a GPU, but at a certain point we need to communicate the data processed on each GPU. So what we could do is, okay, we download the data from the GPU row from the GPU side, from the GPU hardware to the CPU, and then we communicate the data, and then we upload again the data from the CPU to the GPU. This approach is called data staging, and of course, you can imagine that this approach is not efficient because CPU, GPU data movement are expensive, as we mentioned at the beginning. However, there is a technology that you can exploit in, say, most of the recent network, which is GPU Direct. GPU Direct is a technology which provides direct communication between GPU memories. It is called GPU Direct peer-to-peer if it is intranode, and RDMA if it is among different nodes. And in this case, you don't have to move the data on the CPU to implement the communication, but you can directly implement the communication, move the data from one GPU to another. From an MPI perspective, basically, this means that you can provide to the MPI API directly the buffer on the GPU. So in this way, the computation can continue without an expensive update. How to instrument programs with MPI and to instrument the programs to trace those MPI. So first of all, we can choose if we want to generate one report per GPU and sys profile in between MPI launcher and the executable. If you want to generate a single report for all the MPI tasks on the node and sys profile and then the MPI launcher. Be careful because this option is available only if you are as far as I know, if you are doing single node jobs. If you have a single node jobs. If you want to measure only one MPI task because maybe you don't want the information for all the MPI task for some reason, then you can use a wrapper which basically activates the nsys profiler only for one specific rank. If you want to instrument MPI, you need to specify that to the nsys daemon with --3 SQL MPI, and this will provide meaningful information on the time spent in MPI routine, the size of the data transferred by MPI calls, and also the CUDA backend if the communication is GPU aware, which means that it uses GPU direct peer-to-peer or RDMA. So regarding an additional metrics, very interesting metric, an additional option, which is very interesting, is this --NIC matrix true, which provides the throughput of the network card interfaces for multi-node communications. Now, also in this case, we have a simple example. This is exactly the same toy code we saw for single GPU porting. In this case, in our do loop, there is a call to routine, hello swap, which exchanges basically the borders of the local MPI domain with send receive operation. The hello swap basically does the send receive operation to exchange the data of the borders of the grid domain, local grid domain among MPI tasks. Now, I want to show you the difference and how you can detect if awareness has been actually implemented. And to do that, let's see how the report looks like for the first case. So in the first case, sorry, let me just quickly show the report. Sorry, the source code. So at the beginning, we do a non-aware implementation. So we update the buffer on the host, and then we update the buffer on the device. Like in our routine allo swap, for example, as I'm using OpenSCC, I have this update self-update device before and after the MPI communication. If I use this approach, then this is how the report might look like. Now, you see that I have to zoom a lot because I have a lot of iteration steps. Now, first of all, here we have our Jacobi. This other loop is the copy back, basically. And then we have this region. Let's focus on it, where there are MPI communication, MPI send receive. This is, here I've generated one single report per MPI task. So this is the report for MPI rank 1. And I can see the send receive communication because I've added -trace equal MPI. I can see, for example, the byte sent, the byte received, source destination, and also the communicator. And I can clearly see my update directives that I've added in the source code to stage the data on the CPU. Now, if we use a status system view and MPI event summary, well, we can also have an idea of how much this MPI, the times in MPI, how much time is spent in MPI. With this GPU summary, we can also see how much time is spent in operation like host to device, device to host, which are very frequent here due to this data stage. But overall, the amount of time spent in this, let's say, implementation of the communication is about 340 microseconds. Now, let's assume that we don't want to stage the data through the CPU, but we want to exploit the GPU direct peer-to-peer. Here I'm running intranode. And to do that, I just, I just use in OpenSCC the clause of data use device, which basically tells to the MPI library that I'm passing the buffer on the device. This is due to the fact that on OpenSCC the variables have the same name. Of course, if you're working with CUDA, you just use as an input the CUDA buffer. Now, if I look at the report, open it. Okay, now, first of all, you see that we don't have the data movement before and after the communication. We have a single MPI send receive. The time has decreased 44 microseconds, the time for the pattern of the communication. And MPI send receive, now they have a CUDA backend where you can see what is called from the send receive communication, like this main copy device to device async, which corresponds exactly to this main copy peer-to-peer. This is a signature of the fact that the communication is actually aware. We will see in a production case that this should not be given for granted. So, but with Nsight system, you can actually check that you have this aware communication intranode. Unfortunately, as far as I know, at least in the last traces I've seen, you can have a signature of intranode communication on the GPU side, like this main copy peer-to-peer, but you cannot see the data traveling through GPU direct RDMA. So if you are communicating among different nodes, you don't have on the GPU side this same signature for, of course, the RDMA communication. But you can have it for peer-to-peer communication. And you also have the CUDA backend, which shows what is called in the background under the hood. Okay. This is basically what I wanted to show, but we will see more regarding communication. Now, I want to conclude this presentation with some example of usage of Nsight system in production use cases. So in this case, we were working on an application, TurboVB, which implements quantum Monte Carlo simulation. This quantum Monte Carlo simulation can distribute computation among many MPI tasks. So a typical production use case offloaded to GPUs uses 64 nodes with 4 GPUs each node. So quite a good scale. But the problem is that the workload for each MPI task was small and resulted in a low GPU utilization when using a one-to-one MPI GPU approach. Moreover, each MPI task was not exhausting the GPU available memory, and the MPI tasks were distributing basically replicas. So in this case, we tested the efficiency of multiprocessor, of launching multiple MPI tasks on the same GPU, more than one MPI task on the same GPU, thus reducing the total number of nodes, together with activating multiprocess service. Multiprocess service is this technology available on for NVIDIA GPUs, which optimizes the use of resources when launching multiple MPI tasks, multiple processes on the same GPU. It basically helps to schedule the activity among concurrent streams. Now, if you are interested in the findings, you can find all the information in this white paper that has been recently published on our media. And basically, with this NVIDIA NPS, we have been able to run with the same time to solution on 16 nodes, okay, instead of 64, thus significantly improving the efficiency, so in terms of cost and in terms of energy consumption. Now, to understand, I can open the trace to show you how we can see the improvement when using NPS with respect to a, let's say, standard run. Now, this is the timeline view of one run on 64 nodes, on Leonardo, of course. In this case, we are looking at the activity on the GPU. As you can see, the code has some gaps in the GPU activity, okay? Sorry, this is a bit confusing, okay? Because if you open it, some information are replicated and it might become confusing. Let's have a single CUDA hardware. You can see that basically we have some activity on the GPU, which is a bit sparse. There are some gaps. There are some data movement, which are eventually, let's say, comparable with the time spent in computation. So now what we tested was to launch multiple MPI tasks, for example, up to 4 MPI tasks on the same GPU. And if we use Nsight system to look at this configuration, you can see this. Now, I've manipulated a bit by pinning some rows in order to make it more understandable, but basically, you can see that here you have, this is the process, these are 4 processes, okay, of the program. Maybe this one is not needed, sorry. Okay. 4 processes of the program. You have also, for each process, you have the corresponding, the same GPU you used. You can see indeed that the address here is the same. Right? So we are using the same GPU. We are launching 4 processes, and NPS is active in the background. NPS is needed because otherwise this setup would not be efficient. And as you can see, you can basically fill the gaps, thanks by using NPS, fill the gaps in GPU activity with GPU activity from another MPI task. You can also have an overlap between computation and computation. The efficiency of this depends on how many resources are available. And you can also have overlap of data movement with computation, also in this case. Okay, so you see that with NVIDIA Nsight system, it becomes very easy to see how much we are improving the utilization in this kind of configuration. And so this is one additional example. So The next example, this is refers to awareness. No, sorry, awareness. This refers to MPI communication. In this case, the result I'm going to show were collected from another during the support of an application in another separate project, but these basically become are a part of the knowledge base of the Epicure support team when onboarding new applications on Leonardo. So I think is relevant to is a relevant information. For example, you can use this parameter, this option, NIC matrix equal true, in order to collect the infinite bandwidth for internode communication. In this specific code, which was distributed for memory reason due to the memory footprint on multiple nodes of Leonardo, there was a communication intensive pattern for data distribution. Communication were GPU aware by design and non-blocking. It basically was implementing a null-to-all communication with a loop of MPI send and receive and wait all. So when we look at the profile by activating this minus NIC metric true, let me just show you the report. Here. Okay. So this is basically activity on the GPU. These are all the MPI instrumentation, event instrumented. And then you can also see the NIC metrics. So you can see basically how much bandwidth is moving through each one of the 4 NIC available on Leonardo, this one. What we observed was that by default, only 2 NICs over 4 were utilized. And this information was basically, I mean, pretty, except for, if you know the time to solution, you can understand that maybe there is something wrong in the communication. But basically, this information, the fact that only 2 NIC over 4 was pretty silent. So, but by looking at the timeline view of Nsight system, you can clearly see that only 2 NIC are utilized. So you see that if we open the NIC, in particular, you can also see the throughput of the bytes received, the throughput of the bytes sent. And these were working at full regime, the first 2 NICs, but the other 2 were basically silent. They had a very small throughput, and so something was the default setup was not appropriate in this case. So after some investigation, we basically understood that this was due to some settings of the UTX library, and we could fix this non-proper usage of the network interface cards by binding the MPI task to the NIC, and then we can now again check if this actually worked, and that's it. So in addition to have an improvement in time to solution, we can check from the profiler that we achieved the goal, because now you see that we have all the 4 NICs working with a pretty high throughput. So this is a code which is in this setup particularly intensive in communication. Of course, this of course has also it reflects also in the time spent in the network communication. In particular, you see here that from 20 seconds we reached the value of about 10 seconds. So an improvement also in the time spent in MPI, of course. Now, another example still related to MPI communication, and in particular related to awareness. This is interesting because, I mean, also in this case, it applies to a specific code that we have profiled on Leonardo with Nsight system, but can be generalized to any code with similar feature. So this code was implementing a code-aware MPI for collectives. It was using the latest UCC library, version 1.6, available with the NVHPC SDK 25.11 for collective communication. And when we, but in the buffer, the MPI communications were using some custom MPI data types. So when we looked at the profile, I need to open. You cannot. Okay. When we look at the profile, okay, we profiled our code. This is still a single process profile. We noticed that you see that if we focus on, for example, this communication, okay, this communication, MPI will reduce, have main copy peer-to-peer. Copy peer-to-peer, so these communications are aware. However, when looking at the statistics, system view, and in particular to the MPI time, here, so if you open, you can see that, so this is, if you open the wrong report, yes, I opened the wrong report, yes, sorry, I opened the wrong report. So when you look at the MPI statistics, so MPI all reduce, we're basically fine. We have main copy peer-to-peer. Okay, main copy peer-to-peer, which is a signature of awareness communication. This is an intranode run. But when looking at the time spent in MPI calls, we noticed that there was a significant amount of time spent in MPI gather B. This run lasts something like 45 seconds, and the total time spent in MPI was more than 28 seconds, and in particular, most of the time was spent in all gather V. So let's check what is happening in all gather V communication. So if I focus on all gather V communication here, I can see that, okay, by design, the implementation is aware, but actually, there is some green event here, which typically means CPU-GPU staging. In particular, this is host to device main copy, which is called under the hood by the library. So the implementation of my code is aware. The library, in principle, is aware, supports gather V communication, aware of gather V communication, but for some reason, the data were staged through the CPU. And this happened in a pretty silent mode because there was no warning about this. But if I open the report, I can clearly see that here the library is staging data through the CPU, differently from what I would expect. So now, to understand more about that, we basically, for example, if you activate this option on the MPI launcher and you inspect the log file, which is something that can be very, very verbose, you will see that the library complains about the fact that the OMPI data type was not supported. And then there was a fallback OLGATHER-V, which was actually used. So it was not using the aware implementation because of the MPI custom data type. So we basically modified the calls in order to use double complex rather than custom data types, and we could improve. And now we could improve, first of all, the time spent in MPI, because now MPI gather V takes much less time, which is a big difference. And just okay. And then you can see that now the gather V is implementing as well peer-to-peer communication, which is these orange events here. You can also see, for example, that here the gather V is spending a lot of time in actually initializing something on the CUDA side. So this is another information that you can get from the profiler. So maybe if you have some slowdown in the API, despite being aware, maybe this can be related to some initialization done in the MPI by CUDA. You can also, with the sampling point, if you want to check which is the actual library used in the MPI communication, you can also have a look at the sampling point. For example, from here, I clearly see that this is using UCC. Now, the last version of HPX MPI use UCC, all of them, but in some versions they use HCOL. HCOL are different libraries, so maybe you want to know if it is using actually UCC or if it is using HCOL. This might depend on the installation. So I think that this sampling point for the MPI communication can be available, can provide valuable information. So I'm sorry, this is just here I just show the difference in time to solution and the improvement achieved with this optimization assisted by Nsight system. So I want to conclude here just by mentioning, because I don't have much time left, that you can actually profile Python codes and you can actually investigate the performance of other communication libraries, in particular NCCL. So if you're working with trainings, Nsight system can be a tool useful for you, for example, as in this case, to understand the level of efficiency of overlap of NCCL communication with some computation, and to see where there are gaps and to try to understand why. So takeaways for this webinar. So Nsight system can be the first step to understand where the time goes, if it is CPU, GPU, or the network also. Thanks with asynchronous programming and multi-stream, you can hide kernel launches and many overhead, and the efficiency can be controlled with the timeline of Nsight system. Do not give GPU awareness in MPI for granted, and nsys is a very useful tool to check if your MPI communication are actually aware, and use NVTX ranges to constrain your measurement to profile short and targeted runs so you can get meaningful results. Here I leave also a link to the user guide, which contains many more information about the tool, which you can look at. And I thank you for your attention, and I leave the floor to you for questions.
Thank you so much, Laura, for this very, very insightful presentation. So now we can move on to questions. Does anybody have a question for Laura? You can write it on the chat. You can unmute your microphone, turn on your camera if you want. Yeah, go ahead, Andrew.
Yeah, so this is not so much a, sorry, the camera's a bit wrong. So it's not such a question, it's more what Lara pointed out about using non-custom data types in MPI. Well, we've seen this in Epicure in at least one project where using a custom data type caused performance problems with the MPI. So this is quite this is something that we've seen quite a lot in Epicure. So it's something worth noting. Thanks, Laura, for the presentation. That was really very nice.
Yeah, I can also add one bit of information, like, for example, this can be the support of aware communication in aware collective communication, especially in OLGATV, can go beyond also that custom data type, because, for example, if you're still using some old versions of HPC X MPI, some collective communications are not supported on GPUs, not even if you're not using MPI custom data type. So my suggestion is to use the tool to check if it is the case, because this might depend on the version of HPX MPI or OpenMPI. Actually, the version of UCC, which are the underlying libraries, and HCOL, if you're still using HCOL.
Okay, so this is something you really have to check. But the example you showed, the custom data type, was not a sparse data type, was it?
Because no, it was contiguous, actually.
It's contiguous, okay.
Yep,
because the project I was thinking out, we were thinking we had an Epicure was a sparse data type, but okay, this is a problem Yeah.
No, it's contiguous.
This is a more general
And
issue.
it was very simple to move from custom to non-custom.
Right.
But yeah.
In the case I'm thinking about, the PI didn't really want to move the data type, but well, anyway. Thank you very much.
Thank you, Andrew. Any more questions? Comments? Well, I'll let you think about any questions that you might have. I actually have one, Laura, if you don't mind. So,
yeah.
More on a high-level perspective, like when you look at a new trace for the first time, what do you usually check first? Are there usual suspects that you initially go to check? What is your process?
So the process is typically for example, I try to exploit either NVTX ranges or the log file of the code to see which is the most time-consuming routine. Then I filter to that specific part, and if it is a distributed program, I check MPI firstly. And then if I understand that MPI is not the issue, then I move to GPU. That's typically, and I check for data movement first, expensive data movement, and then I check for gaps. That's typically what I would check. Of course, it depends a lot on the program, but yeah, if you have a distributed program, I would start from looking at how much MPI matters. If it is not MPI, then, or if MPI has been improved, then let's see if there are some gaps also in the GPU activity, some data movement, and some kernel launches. Expensive kernel launch.
Yeah, makes sense. Thank you. Any question? I guess I can ask another one and let's say learn from your vast experience in analyzing the traces. So like once you identify a bottleneck, how do you decide how do you decide whether it's worth the effort to fix it? Do you have like a rule of thumb for prioritizing which inefficiencies to check or to fix first? How do you decide if it's worth fixing, basically?
Well, as I typically work with distributed programs, I don't focus like on a single run. I try to see how the different metrics, for example, time spent in MPI, if this is the issue, change across runs on different resources. Like maybe is the time spent in MPI programs that increases, or maybe is, for example, if my program is not distributing a lot, but it's using replicas, maybe is the time spent in some serial part that increases when I scale the application, or maybe sometimes it's like the time spent in launching the kernel which increases. So I typically try to, I typically try to combine the profiling with the scaling, and with Nsight system you can generate the report and then generate the profile, and then with other tools for benchmarking, like for example Ube, you can look at specific metrics and how these metrics evolve while scaling. And because I want to optimize basically the major bottleneck for the largest efficient configuration in my scaling, because the relative times might change. For example, if I see that a CUDA launch kernel starts to occupy most of the time, when I scale, it means that, okay, maybe the kernels are becoming too small, maybe the kernel launches are becoming too large. If I see that MBI time increases, then the issue is MPI, and I need to prioritize this. If I see that, if I see that one routine, for example, which is not ported to GPU, start to become visible, then maybe this is also the main issue to scale the application and to support an efficient scaling. So I typically try to combine profiling with benchmarking to see also how the different metrics scale with the resources.
Okay, thank you. Before we close, yeah, Andrew, go ahead.
Sorry, one last question.
Yeah, of course.
Lara, how do you deal with very large traces? So I suppose if you have a bottleneck which only occurs with, I don't know, 100 nodes or something, how do you cope with something like that?
So I have to say that it depends on how large are the runs in terms of time. So use an NVTX, reduce as much as possible the duration of the trace. This helps. And I try to minimize the amount of information collected. Like, for example, tracing OpenACC sometimes is not so important because once you have the GPU kernels, unless you have some latency due to OpenACC, you might focus only on the CUDA kernel. So you just need to trace CUDA. You don't have to trace OpenACC, CUDA, because this is an overhead. Yeah. I remove CPU sampling because this is an overhead. CPU sampling is done by default. And so, yeah, I try to minimize the amount of information collected and the duration of the trace.
Okay. Because otherwise they become enormous, I suppose.
Yes. And see.
Yeah. Okay, thank you.
Maybe one more question before we close. Okay. So if not, you're seeing my screen, right?
Yes.
Yes, we see it. Yes.
Yeah. Well, I just wanted to thank Laura for the very insightful, interesting presentation. And I want to thank everyone for the participation, for the questions. So it's time to close. So before we wrap up today's webinar, we would also like to highlight the upcoming webinar series. There's a series of 5 webinars focused on profiling, and the next webinar will take place in September. So after we've all come very well rested from the holidays, hopefully. And please stay tuned to our communication channels for more information about all Epicure and initiatives. And yeah, thank you so much for joining us. Thank you, Laura, and have a nice weekend, everyone.